First, a question. Victor Cohen, you here today? Victor Cohen. Can I see you for a moment after class?
Yeah, sure.
Thank you. Now, announcements. My strange attire is a consequence of a few months back my experiencing an abdominal hernia on the left side of my lower abdomen. It was operated on. Unfortunately, the operation did not fix the problem. So I have to have the surgery repeated, and this time under more strenuous conditions. The first time the attempt to fix was done laparoscopically, which is a very simple, painless operation. Didn't work. That's the second time laparoscopic repair for hernia on me didn't work. I should have known it wouldn't work this time. The first time was a different hernia. And now the surgeon has to go in there and sew it up with fish line with the intentions of making it stay together. Because I do not wish to envision the possibility of my intestines falling out, so I'd have to carry them around. That's booked for 3 weeks from today. Now then, that's just to explain why I'm wearing this. Tomorrow night's exam is in Turlington. As opposed to Carleton. Okay. And since it's the first time ever, I was afraid of that. Gotta be someplace I can put it. Let's try that. I got a sponge in here, that ought to hold it up. Since the first time ever I've run this 46B term madness, today I made the very sad and unfortunate discovery that we have the 46L final and the 46 final booked for the same time. This cannot be. So, since some folks are in 46L who are not with us in this gathering because in previous term they just were not able to get 46L, my intentions are to keep the 46L on Friday evening. And hope that you folks will all agree to do the 46 final on Saturday, the immediate day after. Gives you another day to prepare and get it taken care of. Because I gotta eliminate the conflict somehow. And unfortunately, I cannot eliminate the conflict until the term is over, and the term isn't over until that Friday. So, all I can say is, regarding what I just said, if anyone among you has legitimate cause for not being able to make the Saturday arrangement, then I will ask that you see me. But the Saturday arrangement will indeed be better for you, because you'll be working during the daytime. I give you all the time you want. Won't have any trouble getting parking place. And we'll operate in here. All nice things. So we proceed. First, a few remarks on chapter 19. Many of you have already experienced conclusion of chapter 19, but you didn't do anything with this stuff. I said what I said because many of you have been in discussion class and have proceeded to the end of chapter 19 for the stuff that comes after this stuff. Some folks didn't get through that. So I'll make comments on the stuff which was not covered by an earlier discussion class today, tomorrow. But in the main, it's just a review of what you've already been exposed to by having been in discussion class today or by being in discussion class next period. I've also discovered that should I ever be called upon to do this madness again, I'll request one of two things. All the discussion classes are before lecture on Thursday, which would then make life very simple. Or the period 6 discussions are moved to period 5 and we have lecture period 6. Either would work. Now, this has no impact on you folks, and unfortunately does not relieve me of the burden of dealing with the present schedule. So we'll proceed as well as and as best as we can. So, yesterday we talked about dissolving silver chloride in ammonia, wrestled with the question which is the stronger Lewis base towards silver ion, found that it's chloride ion, and saw that the silver chloride was effectively dissolved by treatment with the 6 molar ammonia solution simply because the ammonia far out-muscled, ganged up on the chloride ion in the system. But you saw what happened when we attacked the system with hydronium ion. Immediately we got reformation of silver chloride. That looks like silver chloride, doesn't it? I thought you'd say it would. Okay, and above the liquid portion of the system we had smoke. And I asked you what the smoke is. First, I found that many of you didn't even know what a smoke is. You should learn this in 2045. It's a heterogeneous system, heterogeneous mixture. Most smokes are finely divided particulate solids in air. That's what most smokes are, okay? The reason why you see the smoke is because of the presence of the solids. Not the gas part of the system, that's transparent to light, transparent to your vision, okay? Now then, in 46L, early on this term, you did a similar investigation. Assignment 2. You learned that to test successfully for ammonium ion, to test successfully for potassium ion, by precipitation as the cobalt nitrite compound, which you're required to pursue if the system contains sodium ion, because then you can't find potassium ion by flame analysis. But you also found if the system also contains ammonium ion reacts with cobalt nitrite and makes a precipitate which is deeper in color than the potassium precipitate. So if you got sodium ion in the sample, flame test is out regarding testing for K+. And if you got ammonium ion in the sample, then the cobalt nitrite precipitation investigation is not going to be a conclusive investigation unless you take steps to get rid of ammonium ion. What did you do to get rid of ammonium ion? What did you do? Did you put some of the sample in an open crucible and heat the hell out of it? When did you stop heating? That's got nothing to do with time. You stopped heating when? You stopped seeing smoke above the crucible, didn't you? Now then, let's go back to that investigation briefly. If, for example, in the crucible, you had ammonium chloride, given that that's the salt we asked you to perform this investigation with in assignment 2, when you heated the ammonium chloride solid, that's here, okay? Above the crucible you saw smoke, and then when the smoking ceased to form, you look back in the crucible, if you only had ammonium chloride in there originally, the crucible was now empty. Okay so far? What was this smoke? You did this and weren't concerned about what the smoke is? You were just happy the ammonium ion went away. You don't care what happened to it. Polluted the atmosphere over China. What's the smoke? Well, what chemistry occurred? All of which is discussed in the laboratory manual for 46L, assignment 2. When you heat this strongly, what reaction occurred? You forced H plus transfer from this weak acid to this weak base. And when you forced this H plus transfer, this became ammonia gas, and this became hydrogen chloride gas. Gas. So, in this hot atmosphere you created by heating strongly, these two gases left the crucible. What's the smoke? Did you see the smoke was about maybe this high above the crucible, something like that? What was the smoke? You recognize as these gases leave the hot crucible, they're going to cool off as they contact room temperature air. Well, if they cool off, they're going to slow down. And as they slow down, they're also going to clobber each other. Tell me what happens when HCl gas molecules meet with ammonia gas molecules. What happens? They react, don't they? They react to an extent of 100%, don't they? And what do they make? Ammonium chloride solid, that is the smoke. That's what you did in lab. So take off from there. What was this smoke? I ask you to pay attention carefully to PSI, and then you can answer the question. We had silver chloride in here initially. We poured in an abundance of 6 molar ammonia, didn't we? Got the silver chloride to dissolve. Now when I poured in this abundance of 6 molar ammonia, you think all ammonia stayed in solution? Have you ever taken a whiff in the laboratory of 6 molar ammonia? Well, if you take a whiff of that, do it cautiously. You take the cap off the 6 molar ammonia bottle, go like this, pow, you're going to hit the floor. Because the ammonia vapor that you inhale will be great quantity and knock you flat. And acrid, unpleasant smelling stuff. So do you believe that this vaporous atmosphere above the liquid part of the system, which also contained, which initially contained the silver chloride but is now dissolved, you think there's ammonia in this vapor? So we now added the nitric acid solution, didn't we? All right? So here's ammonia in this vapor, through which we are pouring nitrate ion, hydronium ion, and water, right? Isn't that PSI for the nitric acid solution we added? Now the hydronium ions that hit the solution killed ammonia in solution, killed the silver ammonia complex, setting chloride ion free to re-react with silver ion, and boom, came back to precipitate. So what's the smoke? Here's what you're pouring through in an ammonia vapor. A vapor that's rich in ammonia. What's the smoke? I'm listening. Ammonium nitrate. Absolutely. Because the hydronium ions hit the ammonia molecules, turning them immediately into ammonium ions, which glom onto the nitrate ions, and that's the smoke. You pay attention to PSI, you can answer all kinds of questions. You disregard PSI, you can answer nothing about a chemical system. Nothing. Have you heard me say that before? Once or twice. So on we go with this. As a follow-up to hitting silver chloride with the ammonia, now let's consider hitting silver oxide with ammonia. Now then, some of you might have done this in lab. We've recognized that chloride ion makes stronger bonds to silver ion than does ammonia. How do the bond strengths of oxide ion versus ammonia compare to silver ion? Because this issue will answer that. How do you think they compare? Oxide ion towards silver ion. Now, do you believe that the negative charge density of oxide ion is far greater than that of chloride ion? Not only is it a smaller ion, it's -2. It also shows itself on our acid-base table to be the strongest base in our base column. So if you're starting to fight for H+, you better get out of oxide ion's way. But when we start to fight for silver ion, it's a different ballgame. Because when silver ion gets together with oxide ion, the only bonds you can make are ion-ion bonds. But when silver ion gets together with chloride ion, practically speaking, you convert silver ion to silver atoms and chloride ion to chlorine atoms and make a covalent stuff. And I believe you heard me say before that in the world of chemical bonds, covalent bonds are the strongest. That accounts for why silver chloride is not very soluble in water. It's got nothing to do with silver ion chloride ion attractions. It's because when silver ion meet with chloride ion, you convert ion species to covalent species. I mean, you convert silver ion and chloride ion to a covalent species. That's silver chloride. Very stable stuff. So, what do you bet? Oxide ion fighting for silver ion compared to ammonia. How will that competition compare to the ammonia fighting with chloride ion for silver ion? Do you think this will be a lot more of a fair fight? Ammonia fighting for silver ion, oxide ion fighting for silver ion. I mean, silver ion and oxide ion pretty much bond to each other because of ion-ion bonds. Ammonia molecules bond to silver ion because of the formation of coordinate covalent bonds. But there's another wrinkle to the silver chloride story, which as yet we haven't told you. There's multiple bonding between silver atoms and chlorine atoms in that. That's why the covalent bonds are so strong. With silver ion ammonia, all you can get is a single bond at the coordinate covalent bond site. The non-bonding pair supplied by the nitrogen atom on the ammonia lands into one of the empty valence orbitals on silver ion, makes a single bond. With silver ion and chloride ion, you get multiple bonds. If we find time later on, we'll talk more about that. But in any case, so far, we're really just allowing the facts to speak for themselves. Silver chloride is a considerably more stable stuff than the silver ammonia complex ion, even though the silver ammonia complex ion is a very stable stuff. Remember Kf, 1 times 10 to minus 1.7 times 10 to the 7th? Hey, that's over 10 million, that number. A measure of the stability of silver ammonia complex ion. Well, let's do the analysis. If I wish to calculate the solubility of silver oxide in 6 molar ammonia, and I want to find out how much dissolves, then I got to specify a quantity of ammonia solution. We'll take 1.0 liters to make the arithmetic as simple as possible. There's the equilibrium reaction. These are the equilibrium molarities of all the species involved in the system, which correspond to the solubility of silver oxide. And here's the equilibrium constant, chemically written, which to be evaluated requires multiplication by silver ion molarity squared. Silver ion molarity squared, a game we've now played a number of times, which becomes KSP silver oxide times Kf for the silver ammonia complex ion quantity squared. What chemical reaction corresponds to KSP silver oxide? Is it this? Is that KSP for silver oxide? I can't get a measurable molarity of this in water solution. Just like I can't get a measurable molarity of sulfide ion in water solution. When the sulfide ion molarity has got to be small at most, which corresponds then to 100% hydrolysis of sulfide ion. And this is a stronger base than sulfide ion. You're not going to get a measurable molarity of this in water solution, period, end of story. So, we have to recognize that because of the strong base nature of oxide ion, the correct KSP expression for silver oxide, as given to you on the information sheet, is the molarity of silver ion quantity squared times the molarity of hydroxide ion quantity squared. Now we got species whose molarities can in fact be observed. Okay? Now, based on solubility investigations and whatever have you. This is KSP for silver oxide. There again is KF for silver ammonium complex ion, quantity squared, because of the coefficient on silver ammonium complex ion in the equilibrium reaction. If you want to solve it, hey, it might look complicated at first, but it's not, because the fourth root of the K value is equal to the fourth root of the K. Because this is 2s squared times 2s squared. So up top you got 2s. And what have I got below? 6.0 minus 4s to the fourth. So down below I got 6.0 minus 4s. Enough said. There's the value you get. Now then, rather than treating silver oxide with ammonia, let's consider treating silver oxide with straight ammonium ion. This is question 1931, first part thereof. For starters, even though I've written it here, can you recognize why K for this system has got to be larger than K that we got for this system? Why is K for this system guaranteed to be larger than K for that system? Silver oxide plus ammonia. Here we got silver oxide plus ammonium ion. Why is K for this got to be bigger than K for that? There's the K, it's 18. Well, we know we need ammonia molecules to make the silver ammonium complex ion, right? And up there, practically speaking, all we have are ammonia molecules. So for the first mix, we got ammonium molecules attacking silver ion in silver oxide. That's the only chemistry taking place. Pardon me. That's the chemistry taking place with silver ion. The other chemistry is oxide ion reacting with water to convert to hydroxide ion. But when I hit silver oxide with ammonium ion, clearly the ammonium ion will now, rather than water, attack the oxide ion, because ammonium ion is a good deal stronger acid than water. And when ammonium ion in abundance attacks oxide ion, ammonium ion in abundance attacks oxide ion. What are the products? Ammonium ion in abundance attacks oxide ion. What are the products? Ammonia and water. So not only do I have, with the ammonium ion treatment, not only do I have ammonium ion to hit the oxide ion component of silver oxide. As a consequence of that 100% extent acid-base reaction, I now have ammonia molecules to grab silver ions. So in sum, this system corresponds to an indirect double attack. Indirect. Because you don't have any ammonia until first the ammonium ion hits the oxide ion. But you wind up having, in effect, a double attack. Whereas up top, all you got is ammonia going after, you got ammonia going after silver ion, but water, a far weaker acid, going after oxide ion. So I could say that is also a double attack, but this is a far more effective double attack. Because ammonium ion is indeed a much stronger acid than water. Now then, if I attack silver oxide with ammonium ion, recognizing that we will make ammonia molecules as a consequence of this interaction, I can recognize that one of the silver-containing products is the silver ammonium complex ion, because this is a very stable stuff. Now comes a very important stoichiometry question about this system. When 1 mole of silver oxide is beaten up by ammonium ion, I don't care if you've got million moles of ammonium ion. When 1 mole of silver oxide is beaten up by ammonium ion, how many moles of ammonia can you make? How many? When 1 mole of silver oxide is attacked by a zillion moles of ammonium ion, how many moles of ammonia can you make? How many? 2. Well, you got a mole of oxide ion here. So if you convert all the oxide ion to the products we mentioned a moment ago, ammonia and water, the most ammonia you can make is 2 moles. And if I'm going to complex silver ion with ammonia, I need per mole of complex silver ion 2 moles of ammonia. The stoichiometry of this formula tells me that. But in a mole of silver oxide, I got 2 moles of silver ion, don't I? So per mole of silver oxide, if I'm going to complex all the silver ion, I got to have 4 moles of ammonia. And the reaction we have considered, the acid-base reaction, only gives me 2 moles of ammonia. So all the product, silver ion product, can't be the silver ammonia complex ion. Water, of course, comes from the double proton donation of 2 ammonium ions per oxide ion. What's the other product? What goes here? Or if you wanted to write it like this, that's okay. But this is such a weak acid that leaving the water molecules of hydration off the silver ion is not doing any damage to the chemistry of the system, because its acidity is, practically speaking, negligible. So you got to realize, for a system like this, you cannot convert all the silver ion supplied by a mole of this to this. Some of the silver ion is just going to go in solution as silver ion itself. Now the second part of question 1931 says, what if I hit silver oxide with an ammonium ion ammonia buffer, where the respective molarities of these 2 buffer components are each 6 molar? K up there, 0.10. K here, 18. What kind of K am I going to get for this system compared to the Ks I have so far observed?
Larger.
You think it'd be a lot larger? Because in this last system, not only do I have an abundance of ammonium ion to murder oxide ion, I'm starting with an abundance of ammonia. I don't need to make any ammonia in this system. I'm starting with an abundance of ammonia to grab the silver ion. So here, I have the most potent double attack on this stuff compared to what we have so far considered. Which tells us, before we do any K calculation, whatever K is for this system, it's got to be bigger than what we have so far considered. Now let's put 2 other puzzle parts together. Does ammonium ion react with oxide ion to a large extent? Oxide ion reacts with water 100%. Ammonium ion is a stronger acid than water. So ammonium ion reacts with oxide ion 100%. And how stable is this stuff? 1.7 times 10 to the 7th? Daggone stable. So you put those 2 puzzle parts together, you can recognize that the value for K here is going to compare magnitude-wise how to 18. A little bigger? Somewhat bigger? Or damn large bigger? Damn lot bigger. You like that one? Maybe you don't want to use my language. So we'll say, oh, betcha, you better believe a whole lot bigger. How's that? I get 3.2 times 10 to the 8th. Is that a lot bigger? Is this a lot bigger than 18? Slightly bigger? It's over 10 million times bigger. Slightly bigger. You can evaluate the K for yourself. You know how to play the game. So we jump at long last to chapters 20 and 21, which is nothing more than an extension of everything we have so far done. How about that? Because so far we have done nothing but thermodynamics. And this term we will do nothing but thermodynamics. We haven't the time nor wherewithal to approach chemistry at this stage of the game from a rigorous kinetic perspective. Everything you did in 2045 was thermodynamics, or laying the foundation for understanding thermodynamics, except the one chapter in the textbook on kinetics and the few lectures likely that you heard on kinetics, and the one experiment in 45L that I devoted to kinetics. What's kinetics concerned with? Because if you haven't heard this before, there are only two main ways by which a reaction can be studied by chemists. Only two main ways. Thermodynamically and kinetically. That's it. And in many respects, the thermodynamic study is a whole lot simpler, because time is not a factor. Time means nothing, thermodynamically speaking. Nothing. Because what you do thermodynamically is to take a look at the energy and stability of the products and compare that to the energy and stability of the reactants. It doesn't matter how the reactants got the products, and it doesn't matter how long it took the reactants to get the products. And that gives you what you need to do a thermodynamic analysis of a system. That's what an equilibrium constant reflects. Equilibrium constant tells you nothing about how fast a reaction may or may not go. But it tells you what the ratio will be of the products versus the reactants at equilibrium. It tells you about the relative stability of the products versus the reactants at equilibrium. That's what thermodynamics is about. Kinetics is concerned with the speed part, how fast the reactants become products, and the process itself, the so-called mechanism. You know, what structure changes, what valence electron rearrangements took place. And some reactions, I mean many reactions, they take place in the proverbial split second. Proton exchanges. Have we been talking about proton exchanges? A few times. Rate for proton exchange is on the order of 10 to the minus 9 seconds. You want to be able to measure that? 10 to the minus 9 seconds? A nanosecond? That is fast. So you can see the kind of problems we run into when we start to do kinetic analysis of a system, especially if you're dealing with a very rapid reaction. I mean, this is tough. Well, the math which underlies this is far more complex than the math which underlies the bulk of thermodynamics, and the gadgetry you need in a laboratory to do rigorous kinetic analysis. Hey, hundreds of thousands of dollars for this kind of stuff. Well, we haven't the time nor wherewithal to teach you what's necessary to get at kinetics in the classroom, and we're not going to take the money to buy all this fancy apparatus and put you in the lab to do a rigorous kinetic analysis when you wouldn't know how to do it. So just about everything we do in the first year of chemistry, just about everything you do in undergraduate chemistry, is devoted to a thermodynamic analysis of reaction systems. So more on that now to chapter 20 and 21. So far what we've looked at is equilibrium constants, how they're obtained. Now we're going to look more at equilibrium constants and how they're obtained. From a so-called thermodynamic first principle standpoint. This relationship. This is the relationship you really want to get at for any chemical reaction. Because if the reaction in question can proceed under the conditions under which it's being studied, then delta GR, the change in free energy for the reaction, has got to be a negative value. And that means, from a thermodynamic standpoint, the word spontaneous. Spontaneous. It can happen. Example, take a piece of sodium metal and throw it in a beaker full of water. Potassium metal, throw it in a beaker full of water. You know what happens in this mix? You remember in 45L assignment 5 last term, you were asked to watch a film of a very, very famous movie star demonstrating that combination of materials, sodium metal with water in one beaker, and then potassium with water in another beaker. And he said, "Wow!" And needless to say, I am that famous actor. I hope at least some of you remember seeing that, because you were required to do that to proceed with assignment 5. Okay? So do you think when sodium metal meets with water, potassium metal meets with water, and you go, "Bow!" You think that's a spontaneous process? You'd have to put in any heat to make that thing go? All you have to do is bring the materials together. And when materials are brought together and they react, boom, spontaneous. And that's what we want to know, not just delta H. Again, the textbooks are stupid on this. They hit you with this delta H stuff, which is not usable as a criterion for thermodynamic spontaneity. You need delta G. And if you study thermodynamic spontaneity under standard state conditions, a more rigorous, because of its well-defined nature, set of conditions, then you got delta G sub R super 0. Now, regardless of delta G sub R super 0, you learned about delta H sub R super 0 in 2045, at least you were supposed to have. Standard state. What defines standard state conditions? If you're in a laboratory and you're told to run an investigation under standard state conditions, what do you do? How do you construct a system? Well, let's talk about the possible components of a system. Pure solids, and or pure liquids, and or pure gases, and one other possible system component. What can it be? There's only 4 possibilities. Pure solids, and or pure liquids, and or pure gases, and what else? What's the other possible component of a chemical reaction system? I'm listening. The type of possible system component for which I'm fishing is, in the main, the kind of system component we have been dealing with since day one. Solution species. Dissolved stuff, right, in a solvent, right? See? Ammonia, aqueous, silver ammonia complex ion, aqueous, hydroxide ion, aqueous. That's it. There are no other possible system components. How do I establish standard state conditions for a solid, a pure solid? Do you remember? Do any of you remember reading about this in Assignment 7 discussion for 45L? Because I put it there on purpose. Because I'm not waiting for these dumb textbooks to catch up. This is important stuff. You need to know it. So what we had you look at as a bulk of the Assignment 7 solutions, remember that? Solution studies? Was whether or not a solution forms spontaneously under standard state conditions. Because if I talk about forming a solution without establishing the conditions, then I have to understand whenever I take any solid or liquid or gas and put it in contact with another liquid as a solvent, it's got to dissolve. Nothing else can happen. So it's spontaneous. The dissolving process is spontaneous for that mix until saturation is achieved. Then there's no more net dissolving. Okay? So it's a lot more straightforward to look at spontaneous thermodynamic spontaneity from a standard state condition standpoint. So I repeat the question. If you want to establish a system from a thermodynamic standard state standpoint, what conditions must be established? What corresponds to standard state for a pure solid? The pure solid under atmospheric pressure of 1 is by definition in the standard state. Nothing fancy about that. See this calcium carbonate? It's in the standard state. It's pure solid. If I take this to be pure solid, calcium carbonate. It's not pure, it's got some binders in there. But for the moment, let's believe it's just calcium carbonate. Okay? How about liquid, pure liquid? By definition, a pure liquid at an atmospheric pressure of 1 atmosphere or 1 bar, not much difference. Because 1 atmosphere is 1.01 bar. Okay? It's in the standard state. So if you're going to do a standard state study with pure solids involved or pure liquids involved, just put them in. That's all you got to do is put them in. Put Put them in the required molar quantity as defined by the equation for the reaction, which before you do the study you will have written. What defines standard state conditions for a gas? You realize the gas will be above the system? Gases are not as dense as liquids and solids. Right? Okay. What defines standard state conditions for a gas? The gas must be present above the system at a partial pressure of 1 atmosphere. How about that? So if I'm going to do standard state studies on a system which is consisting of two gases, initially, under standard state conditions, what's the total pressure on the system? What is it? Remember Dalton's law of partial pressures? The total gas pressure is equal to the sum of the partial pressures of the component gases, right? So if I got this gas and another gas, two different gases, and they're each there required to be present at a partial pressure of 1 atmosphere, what's the total pressure on the system? 2 atmospheres. So the only remaining puzzle part of this is solute concentration. Now some thermodynamic folks, because of the nature of the investigations they're making, like colligative phenomena and like, they use molalities. You heard about molalities? Well, we're not going to deal with molalities. We're going to stick with molarities. It's all we've done business with. And most solution studies, I am sure, are done using molarities rather than molalities. What establishes standard state for a solute species? It must be present initially in the solution system at what concentration? 1 molar. That's not hard. Right? Now then, the wrinkle in this is to realize when I do standard state studies on a system, I have to have all reactants and all products in the system. All reactants and all products must be in the system initially in the standard state. They have to be there. And then after I construct a system like this, I see what I wind up with at the end of reaction. Because I'm sure you recognize, if I construct a system which initially has got calcium carbonate in it, and 1 molar calcium ion, and 1 molar carbonate ion, these are all in contact with each other, will that system stay as it is? I've now defined it to be in the standard state. I have a system, two-phase, liquid and solid. There's the solid, calcium carbonate. By definition, this is in the standard state. Calcium ion, aqueous, carbonate ion, aqueous, they're each initially 1 molar. There's my system. Will that system stay as it is? What will happen? The calcium ions will... What do you know about the solubility of calcium carbonate? Does it dissolve to a molarity of 1? The calcium ions and carbonate ions will wham, react with each other, and out comes calcium carbonate. So this shows you another problem regarding thermodynamic investigations. I cannot possibly construct this system and have it exist and give me the opportunity to go get my gadgetry and measure the change in energy which takes place as the calcium ions and carbonate ions react merrily with each other to make calcium carbonate. I cannot make that system. As soon as I put calcium ion and carbonate ion together at relative molarities which exceed 1.4 times 10 to the minus 4 in water solution, wham, they react to make the precipitate. So getting changes in free energy for a reaction under standard state conditions cannot be obtained by direct measurement. But they can be readily obtained by this relationship. Now we can derive this. I'm not going to bother with that. I'm just going to ask that you take this as a given. Because we know how to get equilibrium constants, don't we? Hey, for the system we just described. You just take a water solution saturated with calcium carbonate, make measurement to find out the calcium ion molarity in this saturated solution, the carbonate ion molarity in the saturated solution, from which you calculate K, which is KSP for calcium carbonate, right? You put that in there and you get the change in free energy, with T being in Kelvin rather than centigrade. And if I do this at normal lab conditions, T will be 298 K, right? 25 centigrade expressed in Kelvin. And R is the ideal gas constant. With what kind of units for this kind of arithmetic? What kind of units do I want on R to do this arithmetic? Do I want liter atmospheres per K mole? Did you learn that liter atmospheres is an energy unit in 2045? A strange energy unit, but nevertheless an energy unit. What kind of units do I want? Energy units for R. How about joules or kilojoules, right? Because I'm sure when you were in chapter 5 or whatever it is on thermodynamics in 2045, you recognize all the energy quantities were expressed in joules or kilojoules. So we'll use R in joules or kilojoules, just to make the units work out. Now then, water solid becoming water liquid at 25 centigrade. Is this spontaneous? If I put ice cubes here on the bench top, they going to dissolve? I mean, melt? Can I make this go this way at 25 centigrade? No. How can you confirm that? What would you look at regarding material water to conclude matter-of-factly that water liquid cannot be made to become water solid at 25 centigrade temperature? Regarding water itself, what would you look at? I'll give you a hint. It's at the start of chapter 1. In the notes, it's called a phase diagram. And when you examine a phase diagram for water at the start of chapter 21 in the note, because I know you talked about the water phase diagram for water in 2045, didn't you? Now how you understood that is beyond me, because a phase diagram is a free energy diagram. And here's this textbook not wanting to talk about free energy until chapter 20. How are you going to understand this diagram? I don't know. Must be some kind of magic. A phase diagram is a free energy diagram, period. And when you look at that diagram, you'll see at any temperature less than minus 22 centigrade, lower than minus 22 centigrade, I cannot I'm talking about the wrong thing, pardon me. When you look at the phase diagram for water, you will see that converting water liquid to water solid, okay, cannot be achieved at any temperature above minus 22 centigrade. Let me get that right there, above minus 22 centigrade. And the way you get it to become, say, water liquid to become water solid at, say, minus 1 centigrade, what do? Water liquid to become water solid at minus 1 centigrade. Water solid to become water liquid. What would you do to get water solid to become water liquid at minus 10 centigrade? Water solid to become water liquid at minus 10 centigrade. What would you do? Add pressure. Squeeze it. Taking advantage of the fact that water liquid is more dense than water solid. At least the last time I checked, my ice cubes float in my iced tea. Okay? So, with that you could recognize whether or not these processes as written at these conditions are spontaneous, yes or no. Now then, let's talk about these interconversions. Water liquid, water vapor. Can this be spontaneous at 25 centigrade? Water liquid to water vapor, 25 centigrade. Can that be spontaneous? It's about 25 centigrade in here, maybe a little bit less. In my cup I have water liquid. If I make a mark of the water liquid meniscus level right here now, and leave my cup standing on this bench top, and we come back tomorrow and look inside my cup, will we see the same level of water liquid? What will we see? Water liquid level will be lower, or else the water liquid will be completely gone, won't it? Why? Because the water liquid under these conditions did what? It evaporated, didn't it? So don't you dare tell me that this can't be spontaneous in 25 centigrade, because you just told me what's going to happen to my water liquid. It's going to go away. Now let's be somewhat more specific with the conditions. Can this be spont at standard state conditions? Now, if I'm going to study this system under standard state conditions, you remember our conversation just a moment ago? I'm going to have water liquid, the external temperature is 25 centigrade, and in the presence of this water liquid, if I could do this investigation, I would place water vapor, because clearly in my cup right now there's water vapor up here. Just like in this room there's water vapor in here. But in order to study it at standard state conditions, the water vapor would have to be at what partial pressure? 1 atmosphere. Do you know when the vapor pressure of water liquid equals 1 atmosphere? When does the vapor pressure of water liquid equal 1 atmosphere? At what temperature? What temperature? You did this in 2045, put it to use. Normal boiling point temperature. What's the normal boiling point temperature for water liquid? 100 degrees centigrade. Hey, I'm nowhere near that. So if I set that thing up under standard state conditions, the only thing that can happen is water vapor condenses to become water liquid. Nothing else can happen. And it will continue to condense until the vapor pressure of water liquid, the tendency to evaporate, at 25 centigrade, okay, equals the partial pressure of water vapor in the atmosphere. You did this in 2045, I hope. Well, more on that when we get to chapter 21, okay? Now then, look at this at 25 centigrade. Water vapor becoming water liquid. Is this spontaneous under the conditions which are with us in this room? Yes or no? Is this spontaneous under the conditions which are with us in this room? I didn't say standard state. I said under the conditions in this room. Is this spontaneous? You just told me a moment ago, if I mark the meniscus level for my water liquid and we leave it here until tomorrow, I'm going to come back here and I'm not going to see any water liquid. It's all going to evaporate. Well, if it's all evaporating, is this going at these conditions? No. But we just told you, if you look at this at 25 centigrade and these conditions, then it's spontaneous. Because in order for this to go, partial pressure of water vapor must be larger than vapor pressure water liquid at 25 centigrade. And if you look at the vapor pressure table for water liquid, that you'll see in chapter 21 of the notes, you'll recognize that for the conditions which are with us in this room, that ain't possible. Because if this system is at equilibrium in this room, as the weather people call it, we would be under what kind of humidity conditions? Relative humidity conditions. What kind? 100%. I told you all about that the first day of class. Remember that? We'd be sitting here stewing in our own juices. Because as we perspire, there would be no longer any net evaporation of water liquid to water vapor from our body surface. And so as we continue to perspire, more sweat would build up on our body surface and we'd get more gooey and less comfortable. And you'd pretty soon say, to hell with Horvath, I can't stand it in here, and you'd run away. And for me, since I couldn't stand it, I wouldn't even come in the first place. How's that? Now then, second law of thermodynamics. a criterion for thermodynamic spontaneity. Now we have a criterion, and it's based on change in entropy, not enthalpy. There is no thermodynamic criterion establishable on enthalpy and enthalpy change, which again is my main criticism of what the textbooks do with this wonderful stuff. I repeat, what we want to know about a reaction system is, can it go under the conditions under which it's being observed? Okay? This says, the total change experienced by the universe, everything, for every spontaneous change is always positive. Always positive. And we're experiencing spontaneous changes all the time. And we're also causing non-spontaneous changes to proceed by changing the conditions. Like we said, at minus 10 centigrade, for example, at minus 10 centigrade, you can make water solid become water liquid by applying pressure. Okay? But if you let that system operate on its own, that's not going to happen. Now then, the change in entropy for the system added to the change in entropy for the surroundings is equal to this change in entropy for the universe. Now, if you don't realize this, it's discussed in chapter 20. And I hope you realize this, but again, if you don't, it's in chapter 20. These two delta S changes can never have the same sign. If this is plus and favorable, this is minus and unfavorable. Or, if this is plus and favorable, then this is minus and unfavorable. Example. Now, to appreciate this example, here's the system. I wrote it someplace and erased it. It's terrible. We got it now back again. Plus, favorable, or minus, unfavorable. Look at this system. Now, before we talk about this further, entropy. One way to define entropy is that it is a measure of the ability of a system or substance to distribute its internal energy. The more effectively the system or substance can distribute its internal energy, the higher is its entropy. Now, this also relates to statistical probabilities and energy states and all kind of stuff, none of which we're going to consider now. We're going to get an entropy and changes in entropy from the simplest possible standpoint regarding a substance like water. Tell me, if I say to you that the greater the dynamic character of a substance, the higher its entropy, then you can recognize water solid, water liquid, water vapor. Okay? 3 phases of water. Which is the most entropically favored phase? Vapor. And the least entropically favored phase is solid, because now those particles are locked together with each other in the ice crystal. They can't move. Hardly. Entropy hates that. Entropy likes, woo, let me move around and go up and down, be a gas. That's the best, highest entropy phase, okay? But when you're locked up like this, entropy says, I hate that. Now then, when you measure delta H for a reaction and find that the reaction is exothermic, what have you learned about the energy of the products compared to the energy of the reactants? Or how about stability? What have you learned about the stability of the product compared to the stability of the reactants for a reaction which is exothermic? The products are more stable than the reactants. That's a bond-forming process or a bond-improving process to the minimum. Products are more stable. Okay? In general, there are exceptions. Entropy doesn't like that. Entropy wants this motion freedom business. So I've always argued a very simple practical way to realize that entropy and enthalpy are real properties of the world in which we live, of the universe in which we live. Look around. Do we see gases? Yeah. Do we see liquids? Yeah. Do we see solids? Yeah. And for water itself, under changing conditions, you can see water liquid, water vapor, water liquid vapor equilibrium, water liquid, water solid, water liquid equilibrium. You can even see triple point where all the phases are there. Okay? So in the main, from a thermodynamic standpoint, the universe is an example of the perpetual ongoing fight between entropy and enthalpy. Because if entropy was the exclusive thermodynamic force, there would be no solids, there would be no liquids, there'd be no bonds. Everything would be just this ill-defined vapor, if anything. But if enthalpy had its way, the Big Bang, if that's true, would have never happened. Because enthalpy says, I like bonds. So, enthalpy says, let me be like this. And entropy says, let me be like this. Okay? So we go back to this. If I put water liquid in my refrigerator freezer at -10 centigrade, a likely operating temperature for your refrigerator freezer at home, will it naturally become water solid? Will water liquid become water solid in your refrigerator freezer at this temperature? You betcha. Is this change associated with a favorable positive change in entropy or an unfavorable negative change in entropy? Unfavorable, you betcha. Del S is minus for this thing. Okay? Now then, delta S equals delta H over T for a phase change. I'm just giving you that as just take it as an accepted statement, okay? For a phase change. It doesn't work for anything but a phase change. Okay? Now then, if this occurs in your refrigerator freezer, which it will at that temperature if you put water liquid in there, at what temperature is the water liquid becoming water solid? At what temperature is the water liquid itself becoming water solid? If I take a beaker, water liquid, I put it in my refrigerator freezer at -10 centigrade. Okay? As time passes, this becomes just ice. All right? At what temperature did the water liquid? 0, right? Centigrade? That's the melting point temperature for, we're assuming 1 atmosphere pressure. I don't think in your refrigerator freezer at home you got a pressure this device on the freezer compartment. Okay? All right? So for the change experienced by the system, okay, delta S is delta H for this conversion over 273. That's the temperature in Kelvin. Okay? Now, in order for this to take place, the water liquid must gain heat or lose heat. Is this an exo or endo change? Is it an exo or endo change? Exo, bond forming, you betcha. If you think the bonds in water liquid are stronger than in water solid, next time you go swimming, fill up your swimming pool with ice cubes and dive into that. Ow! Bonds are a lot stronger between the water molecules, among the water molecules in the solid, right? Okay? So, this is exo. Energy liberating. Well, where's the energy going to? It's going to the freezer compartment, right? That's the surroundings. So delta S, this is delta S system here. Now let's try this for delta S surroundings. The same change in energy will take place. The change in energy for this transformation, period. But at what temperature is the freezer getting this energy? At what temperature is the freezer getting this energy? The freezer's not at 0 centigrade. The freezer's at minus 10 centigrade, isn't it? 263 K. So it's the same change in energy associated with each change in entropy, but the system is doing this at 273 K, and the surroundings doing this at 263 K. And this delta S is plus, whereas this delta S is minus. And this is a smaller number than this, isn't it? This is a bigger number than this. You're dividing the same delta H here by a smaller number. So here, when I add delta S surroundings, which is plus, to delta S system, which is minus, I wind up with a plus number, don't I? Keeping with this being spontaneous at the conditions which are with us in the refrigerator freezer. Now, a practical example of entropy. See that? It's a piece of rubber tubing. All right? Now, while you stare at this, I want a quick sketch, a formula on the board. The sticks all represent bonds to hydrogen. Here's a ball and stick model. Remember that these carbons are all sp3 hybridized. So this is hardly a linear molecule, even though the picture on the board suggests that it's linear. Okay? Here's what it looks like. Okay? All these sp3 carbons, so 190-degree bond angles all over the place, stuff like that. Now then, look at this, what's on the board. And look at this. For starters, do you see these formulas are of the same composition? These are isomers. Which isomer has the higher entropy and why? This one or that one? You see, this is the more tied up form. When this thing wiggles, it can wiggle along a carbon chain that's 1, 2, 3, 4, 5 atoms long. When this thing wiggles, its longest possible wiggling action is over a carbon chain that's 3 atoms long. Okay? So this is this. Oh, but look at how it came apart, and look at all the things it can do now. Wiggle all over hell. Because now it has a much higher entropy. Pick it up from this point tomorrow.